So here above we have our logarithmic formula for integrating logarithmic functions. You can read that over, but basically this tells us that the integral of 1 over x dx is equal to the natural log of the absolute value of x. People will often forget that there's an absolute value sign there, so be careful about that, plus the integration constant. So let's go ahead and move on to example 5. It wants us to evaluate the integral of 5 over 5x minus 2 dx. And I'm going to make my u value 5x minus 2, and then du will equal 5 dx. And we don't need to do anything there, so we can rewrite that integral as du over u, which is the same thing as this integral here. 1 over u times du is the same thing as du over u. And so that tells us, according to this formula up above, that that will be equal to the natural log of the absolute value of u plus c. And then we can substitute back in the u value. So the natural log of the absolute value of 5x minus 2 plus c. And that is our final answer there. Example 6 says evaluate the integral of x minus 3 over x squared minus 6x plus 1. Here I'm going to make my u value x squared minus 6x plus 1, and then if I take the derivative, we're going to get 2x minus 6 dx. Now, notice that there is no 2x minus 6 anywhere in our function that we're integrating. However, what I could do is I could factor out a 2 here. So I could do du equals 2 times x minus 3 dx, and then if I divided both sides by 2, then we'd see that du over 2 is equal to x minus 3 dx. And I have an x minus 3 dx here, so I can replace that all with du over 2. So I'm going to rewrite my integral as du over 2, and then the rest of it is just 1 over u. Maybe I'll put this on the other side, 1 over u times du over 2. And if I rewrite that, that's just 1/2 times the integral of du over u. So that will be 1/2 times the natural log of the absolute value of u plus c. And then that will be 1/2 times the natural log of the absolute value of our u value, which we decided was x squared minus 6x plus 1 plus c. So that concludes example 6. Example 7 says, because the world contains only about 10 billion acres of arable land, world population is limited. Suppose that world population is limited to 40 billion people and that the rate of population growth per year is given by dp dt, which is equal to k times 40 minus p, where p is the population in billions at time t and k is a positive constant. Then the relationship between the year and the population during that year is given by the integral t equals 1 over k times the integral of 1 over 40 minus p dp, where 40 minus p is greater than 0 because 40 billion is the population's upper limit. Part A says evaluate this integral to find the relationship. So this is part A. We have that t equals 1 over k times the integral of 1 over 40 minus p dp, and I'm going to make u equal to 40 minus p, and then du is going to equal negative dp. And so we would then rewrite this as, so if du equals negative dp, if we multiply both sides by -1, then we get negative du equals dp, like that. And so we'll end up getting the integral of, let's see, 1 over u times negative du. And then we can take out that negative sign, so we'll get equals negative 1 over k times the integral of du over u. and that's equal to negative 1 over k times the natural log of u. I'm just going to go ahead and substitute the u value in. So it's going to be 40 minus p, like that, plus our constant of integration. So finally, we get that our function is t equals negative 1 over k times the natural log of 40 minus p plus c. And I'm going to label this c sub 1, and you'll see why once we do the next portion. But this is our function or our relationship for part A. Part B says use properties of logarithms and exponential functions to write p as a function of t. So let me just rewrite the function we found in part A. T equals negative 1 over k times the natural log of 40 minus p plus c1. Now, the first thing that I want to note is that we can drop the absolute value signs because it says that 40 minus p is greater than 0 in the initial problem. And we can't take the natural log of a negative number. So that's why the absolute value signs are there. But since 40 minus p is always going to be positive, we can drop the absolute value sign. So I'm going to rewrite this as t equals negative 1 over k times the natural log of 40 minus p plus our constant. Now, our goal is to solve for p, so I'm going to subtract our constant on both sides. So I have t minus c1 is equal to negative 1 over k times the natural log of 40 minus p. And then what we want to do is we want to multiply both sides by negative k. So if we do that, we get negative k times t minus c1, or c sub 1, and that's equal to the natural log of 40 minus p. And so, again, we're solving for p. Now we need to use the exponential form of the logarithm. So if I rewrote this in exponential form, we would have that 40 minus p is equal to e to the negative k times t minus c1 power, like that. I'm going to distribute in the negative k into the exponent. So if we did that, we get 40 minus p is equal to e to the negative k t plus k times c1. And then using properties of exponents, we can rewrite this as e to the negative k t times e to the k times c1, like that. Now the reason that I wrote c sub 1 is because this thing here, all of these are constants, and so I can just rewrite this as another constant c, and that's why I didn't want to confuse you with the c1. So this can all just basically be, compiled together and just be called c, like that. So if we continue on in our quest to solve for p, then we get here that 40 minus p is equal to c times e to the negative kt power. And then we can, we can subtract 40 on both sides. And so we get negative p is equal to negative 40 plus ce to the negative kt. And then if we multiply everything by negative 1, we get p equals 40 minus ce to the negative kt power. And that is our final answer for part B.